Hello, I'm Srisha Chakraborty and I'm an applied machine learning researcher at USRA, and I'm also a part of NASA's Black Marble Science team, and I'll be presenting our work on nightlight-based assessment of global electricity infrastructure and future emissions to meet growing demand. I would also like to highlight the amazing team members that I work with for this project. The electricity infrastructure intersects and adversely impacts different parts of the Earth system components. And yet it remains crucial for development and society and is central for human health, security, and food production. Access to electricity also remains one of the key sustainable development goals. Moreover, the electricity demand is expected to rise. At present, there are 675 million people who live without electricity access. Continuing urbanization in these low-access areas and increased heating and cooling demand due to climate change is expected to contribute more towards this rise. International development goals have prioritized universal reliable electricity access, and yet it remains a monumental challenge to close the existing gaps, meet the growing demand, and yet minimize the negative environmental impact of electricity infrastructure. This is mainly because at present we don't even have global, systematically collected yet locally relevant data for informing where the access gaps exist and how the power sector will evolve to address them. So we require spatial and temporal information on electricity access and uncertainties to understand how the power sector will evolve and help in estimating the impact of this infrastructure towards emissions. So the objective of the study is to assess the spatial distribution and degree of electricity access and to inform downstream studies to explore how the future electricity supply will evolve and what its impact on emissions will be. Daily satellite data is used as the basis of electricity access in our study due to its global spatial coverage. The study specifically relies on nightlights derived from NASA's Black Marble product, and the satellite-derived nightlights have a unique advantage in capturing city lights at a global scale daily and forms the basis of our study. Our workflow to address this consists of 3 steps: satellite-based information on electricity access, on electricity reliability, followed by downstream energy modeling studies. Here we'll discuss the first 2 satellite-based analysis steps. Electricity access will give a binary decision on whether or not pixels have access to electricity and will highlight the regions of ongoing development and the regions with access gaps. Electricity reliability will tell us about power access frequency and consistency based on the stability of the time series data. These satellite-derived products are at a 1 kilometer resolution globally for a decade, and therefore the complexity and the volume of the data requires us to use advanced computational methods such as machine learning. To tackle the geographic and temporal variation in the data, we want our methods to be generalizable, our approach to be generalizable. To tackle the scarcity of high-quality labels or the lack of high-quality labels, we want our methods to be unsupervised. And we also need to be able to produce estimates of decision trust so that downstream users can use our data products reliably. For the first step in understanding electricity access, we take the Black Marble data and mask it over urban areas to detect pixels of consistent electricity access from 2012 to 2022 using rolling windows based on a detection threshold. This threshold is tuned on survey data based on percentage of population electrified. This derives a binary data set of whether or not a pixel has electricity access and gives the date of electrification. This dataset also highlights the sites of ongoing electrification and the sites of current electricity access gap. We then move on to electricity reliability by learning a data-driven model to characterize the variation in the stable baseline phase over successive NTL windows using neural network architectures suitable for handling sequential data. Our approach is unsupervised, and the model learns the natural variations in the baseline and adapts across geographies to learn region-specific models. The trained model is then applied to incoming data to derive predictions. We get an ensemble decision using the average of all 7 neural network models, and if the model predictions match the observations, we say that the grid state is reliable, but if the observations deviate from the model predictions, then we say that the pixel likely has interrupted energy access and the grid state is unreliable. An example of this model is seen through the damage to the power grid caused by Hurricane Maria. The time series captures the rich variation over time. The unstable grid behavior and the prolonged outage caused by Maria is seen in the NTL drop. We see the high prediction error that allows detection of grid instability, and this model helps in deriving a binary decision on grid state, the severity of the outage, the number of consecutive days of outage, and also derives decision confidence based on ensemble agreement that establishes trust for downstream analysis. Our ongoing work includes generalization over several examples of unstable grid behavior. What's noteworthy is the impact of the power grid on people. For example, Hurricane Maria in New Orleans impacted more than 1 million people through power loss initially, and then 98% of the residents were still without power after a week in 85 degrees heat. We are collecting these examples and training the models across these sites to have a spatially invariant models. We're also deriving data sets of power access frequency and consistency. To conclude, machine learning estimates NTL behavior accurately. It monitors the grid stability and detects unstable grid state over urban areas. With these data sets, we're also deriving additional metrics on data quality and decision confidence to ensure trust. And we're sharing the data sets using AI/ML ready format. Future steps would include integrating these data sets with energy modeling studies. Thank you very much for your attention, and please do not hesitate to get in touch if you have any questions.